Right now, without feeling it, without any sensation whatsoever, you are moving at over 1,000 miles an hour. The ground beneath you is spinning, the star you orbit is spinning, the galaxy containing that star is spinning, and the subatomic particles inside every atom of your body carry an intrinsic rotation that cannot be removed, slowed, or switched off, not by any force in the universe. From the smallest thing physics can measure to the largest structure the universe has ever built, everything is rotating. That is not a poetic observation. It is one of the most precise, well-confirmed, and deeply unexplained facts in all of science. And once you understand why it's true, you will never look at the night sky the same way again. If you enjoy deep space explorations like this, consider subscribing. To understand why everything spins, we have to go back, not just to the beginning of the solar system or the beginning of galaxies, but to the physical principles that were baked into the architecture of reality before a single star had ever ignited. Because the answer is not a matter of coincidence, it is a matter of geometry, of conservation, and of the profound stubbornness with which the universe refuses to let certain quantities simply vanish. Let's start with what might seem like a simple observation, and then slowly strip it of its simplicity. When you watch a spinning top, you're watching something that was set in motion by a deliberate act. Someone twisted their fingers and gave it angular momentum. When you watch a planet orbiting a star, the same basic physics applies, but the originating act was not a hand. It was gravity and the slow collapse of an enormous cloud of gas and dust across millions of years. In both cases, angular momentum had to come from somewhere, and in both cases, once it existed, it went nowhere. This is what physicists mean when they say angular momentum is conserved. It does not decay. It does not spontaneously evaporate. In a closed system with no external torque, the total angular momentum remains constant forever. Not approximately constant, not constant-ish. Exactly, precisely, permanently constant. This is not an empirical observation waiting to be overturned by better measurements. It follows directly from the mathematical structure of space itself, specifically from the fact that the laws of physics do not change depending on which direction you're facing. This connection between symmetry and conservation was formalized by the mathematician Noether in 1915 in what is arguably the most important theorem in all of theoretical physics. Noether's theorem tells us that for every continuous symmetry in the laws of nature, there is a corresponding conserved quantity, translational symmetry. The fact that the laws of physics are the same everywhere in space gives us conservation of momentum. Time symmetry. The fact that the laws of physics are the same at every moment in time gives us conservation of energy. And rotational symmetry. The fact that the laws of physics are the same, regardless of orientation, gives us conservation of angular momentum. The universe spins because the universe is rotationally symmetric. These are not two separate facts. They are the same fact, and seen from two different angles. But knowing that angular momentum is conserved does not explain where the rotation came from in the first place. For that, we need to talk about something called tidal torque theory, and about the extraordinary thing that happens when gravity acts on matter that is not perfectly uniformly distributed. The very early universe was not perfectly uniform. This is worth pausing on because it is one of the most consequential facts in all of cosmology. In the first fractions of a second after the Big Bang, the cosmos was flooded with energy in a form so dense and hot that our physics can only approximately describe it. But embedded in that dense, hot plasma were tiny quantum fluctuations, microscopic variations in density that were seeded, according to our best current models, to during an epoch of exponential expansion called inflation. These fluctuations were extraordinarily small. We're talking about density variations on the order of 1 part in 100,000, but they were there, and as the universe expanded and cooled, gravity began to amplify them. Regions that were slightly denser than average attracted slightly more matter, which made them denser still, which attracted more matter, in a feedback loop that eventually produced the cosmic web, the large-scale structure of filaments, sheets, and voids that defines the universe at its grandest scales today. The seeds of galaxies, of stars, of planets, of you, were all planted in those primordial density fluctuations, and those fluctuations critically, were not arranged in a perfectly symmetric pattern. They overlapped. They exerted gravitational forces on each other from varying distances and varying directions, and when a gravitational force is applied off-center relative to an object's center of mass, it does not merely accelerate the object, it rotates it. This is the essential mechanism of tidal torque theory. As regions of the early universe were collapsing under their own gravity to eventually form the first proto-galaxies, they were simultaneously being tugged by the tidal gravitational forces of neighboring overdense regions. Because those neighbors were distributed asymmetrically, the net effect of all those tugs was not zero. It had a preferred direction, and so the collapsing protostructure began to rotate, not because someone pushed it, not because the universe started out spinning, but because asymmetric gravitational forces, yet acting on asymmetric distributions of matter, inevitably produce rotation. And once that rotation existed, once that angular momentum was acquired, it could never be undone. The universe's commitment to conservation ensured that every galaxy that formed from that process would carry the rotational signature of those early gravitational interactions, preserved across the entire history of cosmic time. Our own Milky Way galaxy is a product of exactly this process. It is a barred spiral galaxy, roughly 100,000 light-years in diameter, containing somewhere between 100 billion and 400 billion stars, and it is rotating. The Sun, along with its entire retinue of planets, moons, comets, and asteroids, orbits the galactic center at a speed of approximately 220 kilometers per second. And at this speed, it takes roughly 225 to 250 million years to complete a single orbit, a period that astronomers sometimes call a cosmic year or a galactic year. The last time the Sun was in its current position relative to the galactic center, the dominant land animals on Earth were the first dinosaurs. The time before that, it was the Permian period, just as life was recovering from the most catastrophic mass extinction in Earth's history. The galactic year is a unit of time so vast that our entire written civilization would barely register as a rounding error within it. And yet, the Sun has completed this circuit approximately 18 to 20 times since it formed 4.5 billion years ago. The galaxy is not young. It has been spinning for a very long time. What is particularly striking about our galaxy's rotation is something that took astronomers decades to fully appreciate. It does not rotate like a rigid disk. In a rigid disk, like a vinyl record or a spinning coin, the entire surface rotates at the same angular velocity, which means the outer parts are moving faster in absolute terms than the inner parts, but they all complete a rotation in the same amount of time. The solar system is a good example of this kind of behavior. It does rotate somewhat like a rigid body near the Sun, but a galaxy does not. In a galaxy obeying only the gravity of its visible stars, you would expect the orbital speeds of stars fall off with distance from the center, in the same way that the orbital speeds of planets fall off with distance from the Sun. Mercury moves much faster than Neptune because Mercury needs more orbital velocity to resist the Sun's stronger gravitational pull at its closer distance. You would expect the same pattern in a galaxy. Stars near the galactic edge should be moving much more slowly than stars near the center, but they don't. The rotation curves of galaxies, plots of orbital velocity against distance from the center, are flat. Stars in the outer regions of a galaxy move at roughly the same velocity as stars near the center, which means the outer stars are completing orbits far faster than gravity from the visible matter alone would allow. This was deeply puzzling when Vera Rubin, building on earlier work by Fritz Zwicky, began systematically documenting it in the 1970s. The only explanation that made physical sense was that there is more matter in galaxies than we can see, a great deal more. A matter that exerts gravitational force but does not interact with light in any way we can detect, dark matter. And what the rotation curves of galaxies tell us is that this dark matter is distributed in a roughly spherical halo around the galaxy, extending far beyond the visible disk, a halo so massive that it dominates the galaxy's gravitational field at large radii and keeps the outer stars locked into their faster than expected orbits. The galaxy spins in the way that it does not just because of the stars and gas we can see, but because of a vast, invisible scaffold of dark matter that we have never directly detected, the nature of which remains one of the deepest unsolved problems in all of physics. Within the galaxy, the process of rotation replicates itself at every scale. When dense molecular clouds, the stellar nurseries that give birth to new stars, begin to collapse under their own gravity, they carry their own angular momentum with them. A molecular cloud is typically tens to hundreds of light years across and contains anywhere from a few hundred to a few million solar masses of gas and dust. These clouds are turbulent. They have internal velocity variations, different parts of the cloud moving at slightly different speeds in slightly different directions, that produce a net angular momentum for the cloud as a whole. As gravity pulls the cloud inward, conservation of angular momentum does what it always does. It speeds the rotation up. This is the same principle that makes a figure skater spin faster when they pull their arms in. As the moment of inertia decreases, as the mass is concentrated into a smaller volume, the angular velocity must increase proportionally to keep the angular momentum constant. A molecular cloud that takes 10 million years to rotate once will, as it collapses, progressively speed up. By the time the collapsing gas has concentrated into a disk tens of astronomical units across, an astronomical unit being the average distance from Earth to the Sun, portions of it are completing orbits in thousands of years. By the time the central protostar ignites and is surrounded by a protoplanetary disk, material in the inner parts of that disk is completing orbits in months. The entire process is a lesson in the amplification of rotation by gravity, and it explains why every star system we know of that has been studied in sufficient detail appears to have been born from a spinning disk. The disk itself is important. It's worth dwelling on why collapsed structures tend to form disks at all, because this is deeply connected to why planets end up in orbits within a relatively flat plane, why the rings of Saturn are thin, and why spiral galaxies have the particular flattened shape they do. The reason comes down to the difference between two directions in a rotating, collapsing system: the direction parallel to the rotation axis and the direction perpendicular to it. In the direction parallel to the rotation axis, along the poles, so to speak, there is nothing to prevent collapse. Gravity simply pulls the material inward and it contracts. But in the direction perpendicular to the rotation axis, in the equatorial plane, the angular momentum of the material gives it centrifugal support. It can't collapse further inward without somehow shedding angular momentum. So, collapse proceeds easily along the poles, making the structure flatter and flatter, while it is resisted in the equatorial plane. The result is a disk. This is why protoplanetary disks are disks. This is why the rings of Saturn are flat. This is why spiral galaxies, despite containing hundreds of billions of stars distributed across a volume of space incomprehensibly larger than anything in our daily experience, are thin. The universe is full of disks because angular momentum is conserved, and conserved angular momentum always tends to select a preferred plane of rotation and enforce it. The planets of our solar system are products of this protoplanetary disk. They formed through a process called accretion, the gradual sticking together of dust grains into pebbles, pebbles into larger rocks, rocks into planetesimals, planetesimals into protoplanets, and protoplanets into the full-grown worlds we see today. Because all of this material originated in the same rotating disk, orbiting the young sun in roughly the same direction, the planets that formed from it are also orbiting in the same direction. They are also rotating. For the same basic reason, as planetesimals collided and merged, the asymmetric impacts gave the growing bodies net angular momentum, and they orbit in roughly the same plane because they all formed from the flat disk. This common orbital plane is called the ecliptic, and it is a direct geometrical fossil of the protoplanetary disk that existed around the Sun 4.5 billion years ago. When you look at the night sky and trace the path of the planets across it, you are looking at a record of the disk from which the solar system was born. But not everything in the solar system obeys this simple story perfectly. Venus, for example, rotates in the retrograde direction. It spins backward relative to its orbit and to most of the other planets. Its day is longer than its year. Uranus is even more dramatic. it is tilted almost completely on its side, with a rotational axis inclined at about 98 degrees relative to its orbital plane, meaning it essentially rolls around the Sun rather than spinning upright. These anomalies are not violations of the principle of angular momentum conservation. They are the signature of large impacts, collisions with massive bodies early in the solar system's history that added angular momentum in unexpected directions. Earth itself shows the signature of such an impact. Our moon is large, disproportionately large relative to Earth compared to the moons of other terrestrial planets. The leading hypothesis for its origin is that roughly 4.5 billion years ago, a protoplanet roughly the size of Mars, which planetary scientists have named Theia, collided with the young Earth in a grazing impact. This impact was energetic enough to vaporize a substantial fraction of both bodies, flinging an enormous amount of material into orbit around Earth, material that eventually coalesced into the Moon. The impact also gave Earth a significant obliquity, a tilt of about 23.5 degrees relative to its orbital plane, which is responsible for Earth's seasons. Even the pattern of our seasons, the reason summer feels different from winter, traces back to a collision with a Mars-sized object 4.5 billion years ago. The rotation of our planet carries within it the memory of that ancient catastrophe. The Moon, in turn, is intimately connected to Earth's rotation in a way that most people find genuinely surprising when they encounter it for the first time. The Moon's gravity raises tidal bulges in Earth's oceans and, to a lesser extent, in the solid rock of Earth's crust. These bulges would align perfectly with the Moon if Earth were not rotating beneath them. But because Earth does rotate, the bulges are dragged slightly ahead of the Moon's position. This creates an asymmetry. The tidal bulge closer to the Moon pulls on it gravitationally, slightly accelerating the Moon in its orbit, while the tidal bulge farther from the Moon pulls backward on Earth's rotation, slightly slowing Earth's spin. The net result is a steady transfer of angular momentum from Earth's rotation to the Moon's orbit. Earth is spinning down very gradually on the order of about 1.4 milliseconds per century, a rate that adds up significantly over geological time. Measurements of ancient tidal rhythmites, sedimentary rock layers that record ancient tidal cycles, suggest that 500 million years ago, Earth's day was only about 20 hours long. 1.5 billion years ago, it may have been closer to 18 hours. As Earth slows, the Moon recedes. It is currently drifting away from Earth at a rate of about 3.8 centimeters per year, roughly the rate at which human fingernails grow. This process will continue until the system reaches tidal locking, at which point Earth's rotation will be synchronized with the Moon's orbital period, and both bodies will perpetually face the same side toward each other. The Moon is already tidally locked to Earth. It is why we always see the same face of the Moon. Total tidal locking of the Earth-Moon system is expected to occur in about 50 billion years, long after the Sun has swollen into a red giant and consumed the inner solar system. It is a future that will never arrive for any living thing on this planet, but the physics driving toward it is operating right now. In every ocean tide that rises and falls on every coast on Earth, the Sun itself is rotating. It completes a rotation roughly once every 25 days at its equator and about 35 days near its poles, a phenomenon known as differential rotation, which is possible because the Sun is not a solid body, but a plasma. This differential rotation plays a profound role in solar physics because as the Sun rotates, it winds up and stretches the magnetic field lines that thread through its interior. Over time, this generates an increasingly complex, tangled magnetic field, which periodically breaks through the solar surface in the form of sunspots, solar flares, and coronal mass ejections. The approximately 11-year solar cycle, the periodic variation in solar activity that affects everything from aurora to satellite communications to potentially Earth's climate, is ultimately a product of the Sun's rotation interacting with its magnetic field. A star that did not rotate would not have a solar cycle. It would not have sunspots. Its corona would be dimmer and less dynamic. The warmth and light that Earth receives would still be there, but the entire complex electromagnetic environment that surrounds the solar system and through which Earth moves would be fundamentally different. Life on Earth evolved in the presence of a rotating, magnetically active sun. It is not unreasonable to wonder whether that evolutionary history was shaped in ways we haven't fully mapped by the fact that our star spins. Young stars rotate much faster than the sun. When stars first form, they are spinning rapidly. Some protostars rotate so quickly that they complete a full rotation in just a few days. But as stars age, they lose angular momentum through a process called magnetic braking, in which their magnetic fields couple to the stellar wind, the stream of charged particles flowing away from the star's surface, and carry angular momentum outward. Over billions of years, this gradually slows the star's rotation, and the rotation rate of a main sequence star can actually be used as a proxy for its age, a technique called gyrochronology. A slowly rotating sun-like star is almost certainly an old star. A rapidly rotating sun-like star is probably young. This connection between rotation and stellar age is another example of how deeply embedded rotation is in stellar astrophysics. It's not just something stars happen to do. It's a measurable quantity that encodes information about their history. Stellar rotation reaches its most dramatic expression in the life cycles of massive stars. When a star, more than about 8 times the mass of the Sun, exhausts its nuclear fuel, it undergoes a catastrophic core collapse. The core, which has been accumulating heavier and heavier elements throughout the star's life, suddenly finds itself without the thermal pressure to resist gravity, and it collapses in a fraction of a second. A collapse so rapid that the core goes from roughly the size of Earth to roughly the size of a city in less than a second. The outer layers of the star, which were still in the process of falling inward when the core suddenly became incompressibly stiff, bounce off the collapsed core and are expelled in a supernova explosion that, at its peak, can outshine the entire galaxy. What's left of the core depends on how massive the star was. For stars up to about 20 or 25 solar masses, the collapsed remnant is a neutron star, an object about 20 kilometers across, containing roughly 1.5 times the mass of the Sun, so dense that a teaspoon of neutron star material would weigh around 1 billion tons. For more massive stars, the collapse continues past the neutron star stage and produces a black hole. Now think about what angular momentum conservation means in the context of a stellar core collapsing from the size of Earth to the size of a city. A stellar core that was rotating slowly, perhaps making one rotation every few days, must conserve its angular momentum as its radius decreases by a factor of several 100,000. The moment of inertia drops by a factor of roughly the square of the radius reduction, which means the angular velocity must increase by that same factor squared. The slow, stately rotation of the pre-collapse stellar core becomes, in the newly born neutron star, a rotation rate of potentially hundreds of times per second. The fastest rotating neutron stars known, called millisecond pulsars, rotate at rates of up to 700 times per second. An object with more mass than the Sun, the size of a city, spinning 700 times per second. This is not metaphor or approximation. This is the measured behavior of real objects that exist in our galaxy right now. Conservation of angular momentum applied to the most extreme density transition in the natural universe produces objects that rotate faster than any macroscopic structure we can build or imagine building. Pulsars, rotating neutron stars that emit beams of radio waves from their magnetic poles, are actually among the most precise timekeepers in the known universe. The regularity of their pulses rivals, and in some cases, surpasses the precision of atomic clocks. An array of pulsars distributed across the galaxy, each spinning with extraordinary regularity, can be used as a galactic gravitational wave detector. The pulsar timing array, which has in recent years accumulated evidence of a gravitational wave background permeating the cosmos, a hum of space-time ripples produced by the inspiral and merger of supermassive black hole pairs at the centers of distant galaxies. Rotation is thus not merely a physical phenomenon in its own right. The rotation of dead stellar remnants is being used as a tool to measure the largest scale gravitational phenomena in the observable universe. Black holes spin too. The mathematics of general relativity allows for only 3 independent properties to describe a black hole: its mass, its electric charge, and its angular momentum. Charge is expected to be negligible for real astrophysical black holes because oppositely charged particles would be accreted quickly and neutralize any net charge. So real black holes are described by just 2 quantities: mass and spin. The spin of a black hole is described by a dimensionless parameter ranging from 0, a perfectly non-rotating black hole, to 1, a maximally rotating black hole. Observations suggest that many astrophysical black holes are highly spinning, close to the maximum allowed by theory. This makes sense because the stars and gas that formed them were rotating, and conservation of angular momentum carried that rotation into the black hole. The spin of a black hole has dramatic consequences for its environment. A rotating black hole drags space-time itself around, with it in a phenomenon called frame dragging, or the lens-thirring effect, which has actually been measured around Earth. Our planet's rotation weakly drags the fabric of spacetime around it, an effect detected by the Gravity Probe B satellite. Around a rapidly rotating black hole, the frame dragging is so intense that no particle, not even light, can remain stationary near the black hole. Everything is forced to co-rotate with the spacetime that is being dragged around. The region of space where this occurs is called the ergosphere, and it has a peculiar property. It is possible, at least in principle, to extract energy from a rotating black hole by exploiting the ergosphere. A process called the Penrose process, first described by the physicist Roger Penrose in 1969, allows an object entering the ergosphere to split into 2 pieces, one of which falls into the black hole while the other escapes with more kinetic energy than the original object had. The extra energy comes from the rotational energy of the black hole itself, which is slowed slightly by the process. The rotational energy of supermassive black holes at the centers of galaxies, if it could somehow be extracted, would dwarf the energy output of entire galaxies sustained over billions of years. The spin of a black hole is not just a curiosity, it is an enormous reservoir of energy embedded in the very geometry of spacetime. The jets that erupt from active galactic nuclei, relativistic columns of plasma that stretch for millions of light years into intergalactic space, are believed to be powered, in part, by the rotational energy of the spinning black holes at their centers. The mechanism, worked out theoretically by Roger Blanford and Roman Zanayak in 1977, involves magnetic field lines threading the event horizon of a rotating black hole being wound up by the black hole's rotation and launching plasma along the rotation axis at velocities approaching the speed of light. These jets are the most energetic sustained phenomena in the observable universe, and they are driven by rotation. The most extreme rotational dynamics in nature produce the most powerful energy outputs in nature. The connection is not coincidental, it is fundamental. Let's step back now from these extremes and think more carefully about the structure of angular momentum at the cosmic scale, because there is something important and potentially puzzling here. Angular momentum is a vector. It has both a magnitude and a direction. When we say a galaxy is rotating, we mean it has angular momentum pointing in some specific direction in space. When we talk about the rotation of our own Milky Way, the angular momentum of the galactic disk points in a direction roughly perpendicular to the plane of the galaxy. When we talk about the spins of individual stars and planets, each has its own angular momentum vector pointing in its own particular direction. If you could stand outside the observable universe and watch a time-lapse of cosmic evolution from the Big Bang to today, you would see matter initially distributed nearly uniformly, then gathering into filaments and sheets under gravity, then coalescing into galaxies, then into stars, then into planetary systems. At each stage, rotation appears. At each stage, angular momentum is acquired, not from nowhere, but through the tidal torque mechanism, through asymmetric collapse, through off-center impacts, through the transfer of angular momentum between orbiting bodies. The universe did not start out spinning as a whole. At least, the standard cosmological model does not require an initial angular momentum for the universe as a whole, and observations are consistent with the total angular momentum of the observable universe being zero, or at least consistent with it being indistinguishably close to zero. But within that overall zero angular momentum universe, local structures acquired angular momentum through the interactions of their parts. Conservation ensures that whenever angular momentum appears somewhere, an equal and opposite angular momentum appears somewhere else. The galaxy rotating one way was balanced when the tidal torques were acting. By neighboring structures rotating the other way, the total books balance. But locally, every structure in the universe is spinning. There is something philosophically striking about this. The universe as a whole may not be rotating, but it is as if the universe distributed its non-rotation into a vast symphony of rotating parts, each compensating for the other, each balanced by an opposite across some cosmic ledger that no physical process can cheat. The cosmos achieves its overall rotational neutrality not through stillness, but through an infinite counterpoint of opposing rotations, from the quantum spin of elementary particles up through the rotation of neutron stars and the billion-year gyrations of galaxies. Speaking of quantum spin, let's spend some time there, because it is one of the most fascinating and counterintuitive aspects of rotational physics in the universe, and it is where the story of why everything spins becomes genuinely strange. Quantum spin is a property of elementary particles: electrons, protons, neutrons, quarks, photons, neutrinos, and all the others. It was discovered in the 1920s when experiments showed that electrons behave as though they have an intrinsic angular momentum that cannot be explained by any actual physical spinning of the electron. The name spin is historical and somewhat misleading. If you tried to explain the measured magnetic moment of an electron by imagining it as a tiny spinning ball of charge, you would need the surface of that ball to be moving faster than the speed of light, which is impossible. Quantum spin is not rotation in the classical sense. It is an intrinsic quantum property that behaves mathematically like angular momentum. It obeys the same algebraic rules, it is conserved, and it couples to magnetic fields in the way that classical angular momentum would. But it has no classical analog. Particles with half-integer spin, electrons, protons, neutrons, quarks, are called fermions, and they obey the Pauli exclusion principle. No two fermions can occupy the same quantum state simultaneously. This is the principle that underlies the entire structure of the periodic table: the stability of matter, the fact that solid objects cannot pass through each other. Particles with integer spin, photons, the Higgs boson, the W and Z bosons of the weak force, are called bosons, and they do not obey the exclusion principle. Z bosons can pile into the same quantum state in arbitrarily large numbers. Lasers work because photons are bosons and can be coherently stacked in the same state. Superconductivity and superfluidity are quantum phenomena that depend on the bosonic behavior of pairs of electrons. The difference between matter and light, between solid substance and radiation, between the opacity of a wall and the transparency of glass, between electrical resistance and superconductivity, all of these trace, at a fundamental level, to the difference between half-integer and integer quantum spin. The universe's most basic distinction between the constituents of matter and the carriers of force is a distinction rooted in spin. If there is any deeper sense in which spin is not just something things in the universe do, but something built into the foundations of the universe at a level below which there is nothing more fundamental, quantum spin is perhaps the clearest expression of it. The connection between spin and the structure of matter goes even deeper when you consider what's called the spin statistics theorem. This theorem, derived from the mathematics of quantum field theory and special relativity, states that the statistical behavior of a particle, whether it is a fermion or a boson, is uniquely determined by its spin. Half-integer spin implies fermionic statistics, implies the exclusion principle, implies the stability and structure of matter. Integer spin implies bosonic statistics, implies the ability to pile into a single state, implies the coherent, force-carrying behavior of the fundamental interactions. This is not a coincidence that needs to be separately postulated. It falls out of the mathematical structure of quantum field theory in the context of special relativity. Spin, in this sense, is not an add-on to physics. It is woven into the deepest relationship between matter, force, space, and time. Return now to the cosmic scale and consider another dimension of rotation that often goes underappreciated: the role of spin in galactic evolution. Galaxies are not isolated systems. They interact with each other, merge with each other, tidally disrupt each other's structure. Our own Milky Way is on a collision course with the Andromeda Galaxy, our largest galactic neighbor, approximately 2.5 million light-years away. In about 4.5 billion years, the two galaxies will begin their merger, a process that will not be a dramatic impact in the way we might imagine, since the stars in galaxies are separated by such vast distances that actual stellar collisions during a galactic merger are extremely rare, but a gravitational interaction that will dramatically reshape both structures over a period of hundreds of millions of years. The resulting merged galaxy, sometimes called Milkomeda, will likely be an elliptical galaxy rather than a spiral. The ordered rotation of both spiral galaxies will, through the chaotic gravitational interactions of the merger, be redistributed into the more random, disordered motions of an elliptical galaxy. The beautiful, organized spin of a spiral will give way to a cloud of stars moving in more randomized orbits. Rotation is not permanent. Angular momentum is conserved, but it can be redistributed from organized rotation into disordered motion, a process that is thermodynamically irreversible. Elliptical galaxies, which tend to be old, gas-poor, and no longer forming stars at significant rates, are the graveyard of spiral rotation. They represent angular momentum that has been randomized, its original order scrambled beyond recovery. But within the chaos of an elliptical galaxy, stars continue to orbit the central black hole. Gas, if it is present, can still cool and collapse and form new stars, and those stars will inherit the angular momentum of the gas from which they formed, spinning in whatever plane the local gas was rotating before a collapse. The tendency to form rotating disks is so robust that even in perturbed gas-poor environments, any new gas that arrives from outside, from a satellite galaxy, from cosmic filaments, from somewhere, will tend to settle into a rotating disk structure. Disk galaxies reform after mergers, given enough time and enough cold gas. Rotation is not easily killed. It is the natural state toward which systems with angular momentum and dissipation tend to evolve. The connection between spin and the formation of planetary systems has been brought into sharp focus in the last 3 decades by the discovery of exoplanets, planets orbiting stars other than the Sun. As of the time of this script, we know of more than 5,000 confirmed exoplanets, with thousands more candidates awaiting confirmation. The diversity of these systems has been extraordinary and, in many cases, deeply surprising. We have found hot Jupiters, gas giants the size of Jupiter or larger orbiting their host stars in periods of just a few days, far closer to their stars than Mercury is to the Sun. We have found super-Earths, planets with masses intermediate between Earth and Neptune, a class of planet that does not exist in our solar system. We have found planets orbiting binary stars, planets orbiting neutron stars, planets in orbits so eccentric they look more like comets than planets. We have found systems with multiple planets packed into orbits closer to their star than Mercury is to the Sun, all of them in near-perfect resonance with each other, a gravitational clockwork of extraordinary precision. What this diversity tells us is that the process of planet formation from a rotating protoplanetary disk is both robust and rich. The same basic ingredients, a young star, a rotating disk of gas and dust, can produce wildly different outcomes depending on the initial conditions of the disk, the mass of the star, the presence or absence of nearby stars, the timing of various processes, and a host of other variables. But in every case we know of, the formation of planets begins with the rotation of the disk. The disk is not optional equipment. It is the mechanism through which angular momentum shapes raw material into worlds. Every planet we have ever found, orbiting any star anywhere in the galaxy, is there because a disk was there first, and every disk was there because of conserved angular momentum threading back, step by step, to the tidal torques of the early universe. This brings us to a question that many people find both fascinating and slightly vertiginous, which is the question of what spin tells us about the ultimate fate of rotating systems. We've seen that tidal interactions transfer angular momentum from Earth's rotation to the Moon's orbit, from stars to their stellar winds, from black holes to relativistic jets. We've seen that mergers randomize angular momentum into disordered motion. But is there any mechanism by which angular momentum can be truly dissipated, truly reduced to zero, in any isolated system? The rigorous answer is no. In a perfectly isolated system, angular momentum is exactly conserved forever by Noether's theorem. But in practice, no system is perfectly isolated. Gravitational waves carry energy and angular momentum away from orbiting binaries. The two neutron stars in the Hulse-Taylor binary system, discovered in 1974 and the first indirect evidence for gravitational waves, earning its discoverers the Nobel Prize in Physics, are spiraling together as they lose angular momentum to gravitational radiation. They will merge in about 300 million years, producing a burst of gravitational waves potentially visible across much of the observable universe. When two black holes merge, as detected for the first time by LIGO in September 2015 in one of the most celebrated discoveries in modern science, they are completing a process in which the angular momentum of their orbit was converted into gravitational radiation and, in the final remnant black hole, into the spin of a new, larger black hole. Angular momentum is not destroyed, it is transformed and transferred. The universe's books always balance. But what about the very longest timescales? Timescales so vast they make the current age of the universe look like an eye blink. Consider the evaporation of black holes through Hawking radiation. Stephen Hawking showed in 1974 that black holes are not perfectly black. They emit a faint thermal radiation due to quantum effects near the event horizon, and this radiation carries away energy, very slowly reducing the black hole's mass. A stellar mass black hole would take roughly 10 to the power of 67 years to evaporate through Hawking radiation, a number with 67 zeros compared to the current age of the universe, which is about 13.8 billion years, or roughly 10 to the 10th power years. Supermassive black holes at the centers of galaxies, containing billions of solar masses, would take on the order of 10 to the power of 90 to 10 to the power of 100 years to evaporate. These timescales are so inconceivably long that they dwarf not just the current age of the universe, but the timescale over which protons are expected to decay, the timescale over which all stellar remnants in the galaxy will have cooled to near absolute zero, the timescale over which all matter will have tunneled into black holes or the lowest possible energy states, and the timescale of almost every other process cosmologists discuss when they consider the ultimate fate of the universe. But Hawking radiation carries angular momentum. A spinning black hole emitting Hawking radiation slowly loses both its mass and its spin. In the evaporation of a rotating black hole, the angular momentum it contained, which was seeded, ultimately, by the rotation of the star or gas that formed it, which was itself seeded by the tidal torques of the collapsing proto-galactic cloud, which were seeded by the density fluctuations of the early universe. That angular momentum is radiated away as particles and radiation eventually dispersed into the cold, dark void of the far future. It is perhaps the most extreme possible journey that angular momentum can take from a quantum density fluctuation in the first second of the universe, amplified over billions of years into the angular momentum of a galaxy, then a star, then a collapsing stellar core, then a neutron star or a black hole, then radiated away quantum by quantum over timescales that are to the current age of the universe as the current age of the universe is to a Planck time. The lifespan of the spin from that first primordial fluctuation to the last Hawking photon would be the longest coherent narrative thread in the history of the cosmos. There is also a dimension to this story that concerns the origin of the universe itself. We have described the angular momentum of objects within the universe as arising from tidal torques, asymmetric collapses, and gravitational interactions. But one can reasonably ask, was there any angular momentum in the universe at the very beginning? The standard model of cosmology, the lambda CDM model, incorporating cold dark matter and a cosmological constant, is consistent with a universe that has zero net angular momentum, as previously noted. But some cosmological models have proposed that the universe might have a preferred axis, a subtle anisotropy in the distribution of matter or in the properties of the cosmic microwave background that might indicate a preferred direction of spin. Observations of the cosmic microwave background by the WMAP and Planck satellites have found hints of anomalies, a slight asymmetry between different hemispheres of the sky, an alignment of the lowest multipole modes that some cosmologists call the axis of evil. But these anomalies are weak and controversial, and the consensus view is that they are consistent with statistical fluctuations rather than evidence of a truly preferred cosmological direction. The universe, as far as we can tell, does not have a global rotation axis. Its rotation is entirely in its parts, not in its whole. This absence of global rotation is itself a profound statement. If the universe were rotating as a whole, if there were a cosmological angular momentum, it would show up as a preferred axis in the distribution of galaxies, in the polarization of the cosmic microwave background, in subtle anisotropies in the apparent speed of expansion in different directions. The absence of these signatures tells us that the angular momentum of the observable universe is, at least to within our measurement precision, zero. All the spinning in the universe is local spinning. Every galaxy's rotation is compensated somewhere else in the cosmos by an equal and opposite rotation. The universe spins wildly in every direction simultaneously, balancing its books with exquisite precision. Now let's talk about something that doesn't often come up in discussions of cosmic rotation, but which is deeply relevant to how we think about rotation, time, and causality. There is a class of exact solutions to Einstein's field equations, the equations of general relativity, that describe universes in which rotation plays a global role. The most famous of these was discovered by the mathematician Kurt Gödel in 1949. The Gödel universe is a solution to Einstein's equations in which the entire universe is rotating, and in which the rotation of the universe enables something deeply troubling, closed, time-like curves. In the Gödel universe, it is possible, in principle, to travel in a path through space-time that loops back on itself, allowing you to return to your own past. Time travel, in other words, would be geometrically possible in a rotating universe. Gödel showed this to Einstein, and Einstein was reportedly troubled by it, not merely mathematically, but philosophically. The existence of the Gödel solution demonstrates that the equations of general relativity are, in principle, compatible with time travel, given the right kind of space-time geometry. The reason we don't worry about this in practice is that, as far as we can tell, we do not live in a Gödel universe. Our universe is expanding, not simply rotating, and the global rotation required for closed time-like curves does not appear to be present. But the fact that rotation is deeply enough connected to the geometry of space-time that a rotating universe would allow time travel is one of the stranger corners of this story. Even more exotic is the rotating black hole, the Kerr black hole. Described by the Kerr metric, an exact solution to Einstein's equations, discovered by Roy Kerr in 1963, the Kerr black hole is not merely an object with angular momentum. Its rotation reshapes the entire geometry of spacetime around it. Inside a Kerr black hole, the singularity, the region of infinite density, where classical physics breaks down, is not a point, as in the non-rotating Schwarzschild black hole. It is a ring singularity, extending in the plane of the black hole's rotation, through the center of which, according to the mathematics, it might in principle be possible to pass without encountering the singularity at all. What lies beyond the ring singularity in the Kerr geometry is a region of spacetime that, according to the equations, contains another universe, or, more precisely, an extension of spacetime that is disconnected from our own. leading to what is mathematically equivalent to a different spacetime entirely. There are also regions in the interior of a Kerr black hole where closed time-like curves are present. No one believes that these features of the Kerr geometry are physically real. Quantum effects that we don't yet understand are almost certainly expected to alter the interior geometry dramatically, and the information loss paradox associated with black holes has occupied physicists for decades precisely because the naive application of the equations leads to conclusions that seem physically untenable. But the fact that the rotation of a black hole produces such exotic mathematical features in the space-time geometry is a profound indication of how deeply rotation is intertwined with the structure of space-time itself. Rotation is not just something that objects in space-time do. In the context of general relativity, massive enough rotation shapes what space-time is. Consider also the role of rotation in magnetism. A spinning charged body generates a magnetic field. The Earth's magnetic field is generated by the motion of liquid iron in its outer core, driven by a combination of Earth's rotation and the convection of heat from the inner core, a process called the geodynamo. The coupling between Earth's rotation and the convective motion of conducting fluid in the outer core is what sustains the complex, roughly dipolar magnetic field that protects Earth's surface from the direct bombardment of charged particles from the Sun. Without this rotation-driven magnetic field, Earth's atmosphere would have been eroded over billions of years by the solar wind, as in the same way that Mars's atmosphere was thinned after Mars's core cooled and its magnetic field collapsed. The presence of liquid water on Earth's surface today, the persistence of a thick enough atmosphere to sustain complex life, the fact that you are reading this sentence at all of this depends, in part, on the fact that Earth is rotating, and that its rotation drives a magnetohydrodynamic dynamo in its liquid iron outer core. Rotation is not just a cosmic curiosity, it is part of the machinery that made life on Earth possible. The Sun's rotation similarly drives a magnetic dynamo, as we discussed. Jupiter's rapid rotation, it completes a full rotation in just under 10 hours, despite being more than 11 times Earth's diameter, drives the most powerful magnetic field of any planet in the solar system, roughly 20,000 times stronger than Earth's. Jupiter's magnetosphere extends so far into space that it would appear, from Earth, larger than the full moon if it were visible to the naked eye. The radiation belts within Jupiter's magnetosphere are so intense that the Juno spacecraft, which is orbiting Jupiter to study it, was specifically designed to pass quickly through the most intense radiation zones to minimize damage. The Galilean moon, Io, which orbits within Jupiter's powerful magnetic field, is the most volcanically active body in the solar system. Its extreme volcanism is driven largely by tidal heating from Jupiter's gravity, but the radiation environment from Jupiter's rotation-powered magnetosphere also plays a role in the complex plasma environment around Io. Everywhere in the solar system, rotation generates magnetic fields. Magnetic fields shape plasma environments, and plasma environments influence the geology, atmospheres, and habitability of worlds. We should also speak about the role of rotation in stellar structure and stellar evolution beyond what we discussed earlier. Rotation induces mixing in stellar interiors. Material from different layers gets circulated, distributing freshly synthesized elements from the core into the envelope, and vice versa. This affects the composition of the stellar surface over time, the rate at which hydrogen fuel is processed, and the eventual fate of the star. Rapidly rotating massive stars evolve differently from slowly rotating one. They are more luminous, they lose mass more rapidly through their stellar winds, and they produce different patterns of element synthesis. The most rapidly rotating massive stars can develop a phenomenon called quasi-homogeneous evolution, in which rotational mixing is so efficient that the star remains chemically uniform rather than developing the layered onion skin structure that most stellar models assume. These stars end their lives differently and are candidates for producing particularly energetic supernova and long gamma-ray bursts, the most energetic explosions in the universe, in which a jet of gamma-ray radiation briefly outshines the rest of the observable universe and which are believed in many cases to involve a rapidly rotating central engine, either a magnetar, an extraordinarily magnetized neutron star, or a spinning black hole. Again, the extremes of rotation produce the extremes of energetic phenomena. There is a beautiful thread running through all of this, from quantum spin to galactic rotation to the jets of active galactic nuclei, which is the thread of conservation. The universe enforces conservation laws with absolute rigidity. These laws are not suggestions. They are the structural consequences of the symmetries of space-time, and the universe has no mechanism for violating them. Angular momentum exists in the universe because the universe is rotationally symmetric. Once it exists, it cannot be destroyed. It can be transferred, distributed, randomized, converted into other forms. Gravitational radiation, Hawking radiation, the disordered motions of merger remnants, but it cannot be created from nothing, and it cannot be eliminated into nothing. Every spinning thing in the universe is spinning because something else spun, and something else before that, all the way back to the first moments of cosmological time, when gravity and geometry began to pull unevenly distributed matter together, and the first local angular momenta were born from the sea of nearly, but not quite uniform, primordial plasma. It is worth sitting with the scale of this. The angular momentum you carry as you spin through space on a rotating planet, in a rotating solar system, in a rotating galaxy, is traceable to quantum fluctuations that existed in the first fractions of a second after the Big Bang, amplified and shaped by gravity and by the laws of physics over 13.5 billion years. The rotation of Earth, responsible for our days and nights, for the Coriolis effect that shapes weather patterns and ocean currents, for the geodynamo that sustains the magnetic field that makes life possible, encodes in its precise rate and tilt the entire history of the solar system's formation and of the catastrophic impact with Theia that formed the Moon. The rotation of the Milky Way carrying us along at 220 kilometers per second in our 250 million year orbit of the galactic center is a fossil of the tidal torques that acted on the proto-galactic cloud 4 billion years before the Sun was born. The spin of the electrons in the atoms of your body is a quantum property baked into the fundamental structure of matter itself, responsible for chemistry, magnetism, and the stability of the matter that makes you solid rather than gaseous. Rotation is not a feature of the universe. It is a property of the universe. It is the way that the universe stores, distributes, and conserves the geometrical information embedded in its asymmetric initial conditions and faithfully preserved through all the transformations of cosmic time. If you were asked to design a universe that would naturally produce complex structure, stars, planets, galaxies, the conditions for chemistry, the conditions for life, rotation would be a requirement, not an accident. Without angular momentum, collapsing clouds of gas would fall straight to the center, producing black holes without disks, without planetary systems, without the slowly building complexity of accretion and chemistry that eventually produces worlds capable of harboring life. The disk, shaped and sustained by angular momentum, is the architect of planetary systems. The magnetic field, generated by rotation, is the protector of atmospheres. The tidal coupling, driven by rotation, is the geologist, the climate engineer, the sculptor of planetary surfaces over geological time. Rotation is infrastructure. It is part of how the universe builds things. And then there is this final thought, which connects back to that opening question. When we look at the night sky and see the band of the Milky Way, we are looking along the plane of a disk, a rotating disk of stars and gas and dark matter, 100,000 light years across, moving as a unit through intergalactic space. Every star in that disk is itself a rotating object, many surrounded by rotating disks of planets and moons. Many of those moons are being slowly tidally locked by the rotation of the planets they orbit. Many of those planets have magnetic fields generated by their own rotational dynamics, and threading through all of it, holding it all together into the organized structure that it is angular momentum, conserved, distributed, inherited across generation after generation of stars and solar systems, seeded ultimately by the quantum whisper of primordial density fluctuations in the first moments of cosmic time. The universe is spinning not because something set it spinning from the outside, not because there was some initial push or cosmic hand that gave it a twist. It is spinning because of what it is made of and how the laws of physics cause uneven distributions of matter and gravity to behave. It is spinning because the laws of physics have a symmetry, rotational symmetry, that by mathematical necessity gives rise to a conserved quantity, and that conserved quantity, once created locally, is permanent. The rotation you observe in a hurricane, in a spinning top, in the Earth's polar orbit, in the rings of Saturn, in the spiral arms of a distant galaxy, seen through a telescope, all of these share a common ancestor in the mathematical structure of space itself, in the fact that the universe does not care which way you face, that its laws are the same in every direction, and that from this profound indifference to orientation emerges, by deep mathematical necessity, the spinning, swirling, gyrating, rotating cosmos we inhabit. Everything in the universe is spinning because angular momentum is one of the universe's most cherished possessions, and the universe has never, in the entire history of time, let go of a single unit of it. The figure skater pulling her arms in, the collapsing protostellar cloud, the neutron star completing 700 rotations every second, the supermassive black hole winding up its accretion disk, the galaxy sweeping its spiral arms through space over hundreds of millions of years. They are all expressions of the same physics, operating at different scales, but following the same rules. Rules that have not changed since the first moment there was a universe to have rules, and that will not change until the last Hawking photon leaves the last evaporating black hole, and the cosmos finally, for the first time in its unimaginably long history, goes still. If that moment ever comes at all, some physicists wonder whether even then the quantum spin of the particles in that last Hawking radiation, the intrinsic angular momentum baked into the fabric of quantum field theory, would persist, carrying forward into whatever comes next the universe's most fundamental commitment to rotation, not as a memory, not as a remnant, as a mathematical certainty. The universe, in other words, may not know how to stop spinning, and when you understand deeply enough why that is, you realize it never needed to learn.